Other questions? I'm thinking about it. Yeah.
So are you going to release the test today?
I'll email you between probably, I'm going to go home and get some lunch and have another cup of coffee. Because like I said, my brain's just fuzzy today for some reason. Like, so I'm going to go home, have lunch, a cup of coffee, and I'll email you sometime between probably 1 o'clock and 3 o'clock and say, okay, it's up. I don't think it'll take that long. It shouldn't take that long. It's just, I want to look over it, and it's a matter of, do I look over it first, or is it the 4th exam that I look over? Because I did 4 of them yesterday, so I just want to make sure.
So how long does it stay up again?
Huh? I told you Saturday, or do you want Sunday? I can leave it until Sunday. The only reason I don't want to push it any later than that is because if we do have a homework assignment on Monday, I don't want you to be thinking about the exam Sunday night. Okay, so I'll make it until Sunday, that's fine. Let me do that right now while I'm thinking about it. Otherwise, I will definitely forget that. But I think I have it set so that you have 3 hours from the time that you open it to the time it closes. Okay. Yeah, it's a 3-hour time window. So hopefully that should be enough time that you get it in. Yeah, go ahead. Yeah, so there's multiple choice questions, which are just, they tend to be more conceptual in nature. But then yes, some of the handwritten stuff, there's a place where you can upload the file. So you should be able to take a picture and upload it, or scan it and upload it, or yeah, that kind of. If it really gives you a problem, you can email it directly to me. That just becomes pain in the rear. Okay. Yes, I'm lazy. It's a pain when I get a bunch of emails because they get interdispersed with the rest of the emails I receive, and then I have to sort it out. And then yeah. So I prefer it if you just upload it through the Moodle server, just because then when I grade question 1, I have everybody's response for question 1 all there, and I just open it up and look at it sequentially. But if for some reason that Moodle goes down, hopefully that won't be an issue. But if for some reason it yells at you, you're like, I got to get this in, just email it to me and we'll deal with it that way. Okay, so this will look weird because you'll see a close date, but you won't see the assignment. Okay, 21st. I'll put it at the 21st at midnight, so then you have 4 days to do it. Other questions? So that's set right now. I just need to open it so that you can see. In fact, what I'm going to do is, I'm going to open it right now, but you can't see it, so then I can just, there. Okay. Man, I am struggling today. I don't know what's wrong with me. So, okay, there we go. Did I take? No. There was one time I accidentally took a NyQuil instead of a DayQuil. That one I walked into class in 15 minutes. I was like, okay, just go, because there's no way. I'm not quite that bad, but I feel. Righto. Okay, well, I left you here last time. And in fact, I even left the drawing stuff up. We were talking about parallel plate capacitors. We had already gone through the energy stored. And the last thing that I was highlighting to you was what happens when you insert a dielectric. The idea that when you put in a material, it tends to polarize and therefore decreases the net electric field between the 2 plates. And due to that decreased electric field, you change the electric potential. The electric potential, or the potential difference between the 2 plates, also decreases. That's indicated by the lines being further apart, less steep slope. And because of that, that actually ends up increasing your overall capacitance. So for the same physical dimensions, you can store more charge if you put in a dielectric. Okay. And so what changes in the equations is just simply you can put in an extra term called the dielectric constant. And again, that is a material property. It depends on how tightly are the electrons bound to the atoms within the material. If they're really strongly bound, then you will not get as large of a polarization, and therefore you won't get as dramatic of a decrease. If they're weakly bound, you'll get a larger polarization, and so the electric field will have a larger change. And if you apply too much of an electric field, or if you try to dump too much charge onto these plates, eventually you rip the electron from the dielectric and you end up getting a conducting path from one plate to the other. It's like a little lightning bolt, except it's not through air, it's through the material. At which point that's generally bad, you destroy the capacitor and then you have to go out and get a new one. I don't know if this can happen where you get too much of a gradient across the cell membrane and it destroys the membrane. Can that actually, it seems like biologically that shouldn't happen, but I don't know if that's actually possible. Like if you get too much of a proton gradient across the membrane and then it just, probably not. Biology is so much better than engineering. Like, I mean, like, your body is just so much better at stuff. It's cool. And self-repairing, and self-thinking now. Self-cleaning and self-washing and sometimes it depends on the textbook that you look at. Sometimes instead of writing this lowercase kappa times epsilon naught, sometimes it will just get combined into a single variable of epsilon. Again, indicative of the fact that it's instead of being the permittivity of space, it's the permittivity of the material. And I believe I also mentioned susceptibility or electronegativity will all be kind of the same measure of that value. It's all about how does it change when you expose it to an external field? How does it polarize? That's all I have to say about that. Last question. So the other thing that I was thinking about was we should at least comment or at least mention conceptually what happens, how does the charge know to stop flowing, right? I mean, if I hook, and I've used the symbols here. So two parallel lines that are not equal length, that's supposed to represent a battery. A constant potential supply. So it provides a constant difference in electric potential from the top terminal to the bottom. And then over here, I've just hooked up a capacitor plate. Okay. So let's say that we look at this, this charging of the capacitor at several different times. So initially, when I hook up the battery, okay, you can think of there is an external electric field being applied to the capacitor from the battery. The battery's purpose is to maintain a constant difference of electric potential between the top terminal and the bottom terminal.
Battery on the left or right?
Left. Yeah. Which means it is set up some sort of external electric field. It maintains a constant electric potential. It produces some sort of external electric field. So I apply that external electric field to my system. I'm thinking of the top plate of the capacitor as being the system. And that is what forces charges onto the top plate. This follows along with the kind of the qualitative discussion that I had at the beginning. Now, as I dump more charge onto the top plate of the capacitor, you could think of, well, there's an electric field due to that top plate that starts to grow, right? As I dump more charge onto the top plate becomes more charged, and I could think of, there's two electric fields, say, at the field point right here between. You have the electric field due to the battery, the external source that's trying to charge the capacitor, and you also have the electric field due to the charges that have already been deposited on the capacitor. And of course, you notice that as I deposit more charge onto the capacitor, what happens to that arrow? What will happen to the magnitude of that electric field as I dump more charge onto the capacitor? It'll increase. Remember, the external supply, this one stays the same. The battery provides a constant electric field, if you want to think of it that way. Whereas, as I dump more and more charge onto the plate, this one grows. So when does charge stop flowing? When do I stop putting more charge onto the top plate?
When it technically when the battery runs out or the max of the capacity can take capacitor.
I'm sorry?
It's either when the battery runs out or like the max that the capacitor can hold.
Yeah, okay, so what's the max? I guess a different way to say this is what dictates the maximum amount of charge that the capacitor could hold. Yeah, and we'll assume that the battery will just last forever, which you know is non-physical. But let's assume, I like the idea, yeah. So let's assume that the battery is non-physical, it can just go forever. Yeah. Yeah, and I'm going to change the word charge. I'm going to say, rather than charge, I'm going to say when the field, the external electric field equals the field of the capacitor. So I like the idea. Yeah. So this field, the external field stays the same. It's that this capacitor field increases. And it can keep increasing until you dump. When it hits the maximum amount of charge, those two electric fields will be equal. So let's say you just have a charge on the wire here. It sees the external electric field due to the battery. It sees the electric field due to the capacitor. They are the exact same in magnitude in opposite directions. And so then the charge says, okay, I just chill here. Right? What's the net force on the charge if the electric field is 0? 0. So it just chills there. It's not accelerating anymore. So I could say that corresponds to the maximum charge on the capacitor plate. The maximum charge, the amount of charge that goes on the capacitor plate, will be dictated by, if you will, the strength of the external supply. If I increase the potential drop of the battery, that increases the external field, and that means that more charge will get pushed onto the capacitor plate. Until the two electric fields are the same, and then it'll stop pushing charge on. Again, that's very qualitative. Question. Let's say that I use a 3-volt battery. Just picking a number. Let's say I use a 3-volt supply here. What's the potential drop across the capacitor have to be? If I use a 3-volt supply to charge up the capacitor, what does the potential drop across the capacitor have to be? Three volts. Yeah, 3 volts. Remember, battery, that means the potential difference from the top plate of the capacitor to the bottom plate of the capacitor has to be 3 volts. Which means if I hook up a 3-volt supply and I know the value of the capacitor, I can now say how much charge is on it. Right? I go to Radio Shack, I pick out a 10 microfarad capacitor, I hook it up to a 3-volt supply, I can now figure out what's the charge that's on the capacitor. The difference between the top and bottom plate is 3 volts. Yeah. Yeah. So yeah, excuse me, I'll put this, if, say, for example, we pick up, I said a 10 microfarad capacitor at Radio Shack, and we hook it up to a 3-volt supply, we can now figure out how much charge is actually stored on that capacitor. We'll take our definition of the capacitor. We said the capacitance is defined as the total charge over the change in potential. And so for this 3-volt supply, we can say, hey, well, 10 micro, power of 10 is micro, just out of curiosity.
-6.
-6. 10 to the -6 farads. That's equal to the amount of charge on the capacitor. So something like 10 to the -5 coulombs. Which is a lot, actually. Yeah, I told you, usually you see capacitors. Oh, I'm sorry?
We're doing comp stuff, though.
Oh. The power. We're just gonna mute Alex. Boom. I just flexed. I feel like I should drop something.
Yeah, that saying they're both equal to Q.
Oh, I'm sorry?
Is that saying they're both equal to Q?
They're both equal to Q. Oh! Wait, right here?
Yeah.
Yeah, oh. Warning. You've got two different, I've got two different C's floating around here. All right, right here. What does this C refer to? Capacitance, right? What does this underlined C refer to? Coulombs, the charge. I'm sorry, we've got two C's now. I'm sorry. 10, so what I did was I substituted in. You guys should yell at me. Wow, I only did half the problem. 10 to the -6, I meant for this to be the capacitance. And what did I forget to do? I forgot to multiply by volts, yeah, right? We said the potential drop across it is 3. And that will tell me how much charge is stored. So I get 3 times 10 to the -5. I'm sorry, bird brain. I should have just made it 1 volt and then nobody would have known my shame of forgetting to put it in there. Nuts. And then, yes. For, not to be confusing, but we should be complete. No answer is correct without units. So yeah, so that's the other C in there. Does that answer your question, Isaiah?
Yeah.
Yeah, so be careful. I mean, I already warned you about, this is a case where V does not equal V, which is not V, which of course isn't V or V. This is a case where C and C are, you have to be careful. The contextual clue will tell you, is it the capacitance or is it the unit? Yeah. Mm-hmm. Now, of course, if we want to store more separated charge, you could run out and get a different capacitor and use the same battery. And if I want to store more charge, I could use a different capacitor with the same battery, or I could use the same capacitor with a different battery. Right? I could say, well, I've got a 9-volt battery here at the house. Well, so if I want more charge stored, I could do a 9-volt battery and hook it up to the same capacitor. And that's, I'll go back to the dielectric for a second. There is a limit. You can't just take any old capacitor and hook up any old battery to it. From a practical standpoint. Okay? From a practical standpoint, if you take some wimpy capacitor and you hook it up to Clifty Falls power plant, which I believe transmits at something like 10,000 volts, right? It will say, okay, I'll try to put that much charge on, and it'll force it onto the capacitor plate, and the capacitor plate will say, I can't handle this, and it'll explode. And so that's the practical issue. So usually these capacitors have some sort of rating. They'll say, rated up to 10 volts or rated up to 50 volts. If you exceed If you put more than 50 volts across it, it will blow up on you. And by blow up, I mean, you know, the charges, rather than staying separated, will go from the top plate to the bottom plate. It'll jump across. You won't have to worry about that. We will play physics and pretend that everything is infinitely robust. Okay. Oh, it doesn't matter how much I put across it. It can handle it. It can take it. Yeah.
So is that what happens when like a battery like explodes and the battery gives?
I think it's something, well, so one way, yeah, so one way that you see this is it's just old age, right? Like you just leave it in a drawer and eventually, I think that's just that the sealant goes bad. But another way I think you can do it is that you take a battery and you run a wire from one terminal to the other. Right? So you take a brand new battery, connect the wire from the top terminal to the bottom terminal, and just hold it there. And you'll notice that the wire gets hot, but I believe the battery gets hot as well. So if you take a battery and batteries provide what? Constant potential difference. You got the constant rate. That's, yeah, no, you're good.
One word.
Yeah. So batteries are designed to provide a constant difference in potential, which means they will adjust how much charge they provide so that they have a constant potential. So if you hook up a wire, which does not have very much resistance, and we'll have to get into Ohm's law in a couple slides. If you hook up a wire which has very low resistance, that means that the battery has to provide a lot of charge very quickly. So if you do that, first of all, you'll notice the wire gets really warm because there's a very high current running through the wire. And the second thing is, I think that can cause the interior of the battery to warm up. And so if you leave it there long enough, it could explode. Anybody jump a car recently? Yeah. What do you have to do? Positive, negative, ground. You have to be very careful about the order you do it. Yeah. And I think the instructions say, make sure that this doesn't touch this. Right? So, you got 4 clamps, you got to go like, positive dead battery, positive live battery, negative live battery, ground dead battery, or something like that. Okay, you have to be very careful, first of all, about the order, but also as you're plugging them in, you have to make sure that the two don't accidentally connect. Because what can happen is if they accidentally connect, that's like running a wire from the positive terminal of a battery to the negative terminal directly. The wire will heat up, the battery will heat up really fast, and you run the risk of exploding the battery. Because the battery says, oh, okay, I'm going to provide as much charge as needed in order to maintain the potential difference. And so it'll just, try to dump as much as it can. Yay, nay? So I think that's the other thing, is you can heat up the interior of the battery and literally get it to explode that way. Yeah. I don't know if that answers your question or not. Yeah. All I have to say about that. Battery, hey, there you go. So in our, I'm going to think about our topographical maps again for a second. I like to think about equipotentials as being the lines on a topographical map. And then from that, you can get this idea about the direction of the electric field, and you can kind of go forth from there. So how does a battery play into this? I think of, first of all, I think I say, hey, don't think of it, okay, first of all, positive and negative is not referring to charge. It is referring to high potential and low potential. So the positive side, the positive terminal of a battery is the high potential side, the negative terminal is the low potential side. Does not refer to the charge. Now, thinking about a battery in our topographical analogy, I like to think of it like this. There's some sort of urban witchcraft going on inside the battery that carries charges from a low potential to a high potential. Think of it as like an escalator. You go across the battery. If you're thinking about the topographical lines, you cross a bunch of lines so that you go from low potential back up to high. And what goes on inside a battery stays inside a battery, and it's urban witchcraft. Right? That's all it is, right? There's a little gerbil inside the battery. It's running on a wheel, and it just carries the electric field. No? Okay. Yeah, I mean, of course, there's some sort of chemical potential, or there's a separation of two chemicals. There's an anode and a cathode. And as the chemical reaction goes on, you're transferring electrons from the anode to the cathode. I don't remember. There's a couple pieces of metal in there that are getting oxidized and some other stuff, and you guys know that better than I do, to tell you the truth. Good so far? Yes, of course, a battery is designed to maintain a constant difference in electric potential, and it will do so for long as it can. Of course, you know from a practical standpoint, eventually the chemicals inside the battery, for lack of a better term, get used up, do all of their reactions, and that's the point when the battery dies. There's no additional excess charge to provide. So it can't continually provide the supply of charges. It can't maintain the constant potential difference, and so that's the point when it dies. Right. And usually you'll notice, I think if you take a voltmeter to measure the potential drop across a battery, right? If you do it for a good battery, you should get something like 1.5, 1.6, right? Somewhere in there. If you do it to a dead battery, you usually get something like 0.9. Sometimes if you get one that's in the process of dying, you might get 1.3, but I think like perfectly quote unquote dead batteries, when I measure the potential, you get like 0.5, sometimes 0.9. I don't get 0. But also bear in mind that, say for example, this mouse is designed to operate off a potential difference of 1.5. So even though the battery might still have some energy still stored in it, right? There's a potential drop of 0.9 on the dead battery. That's not enough to operate this thing anymore. So anyway, yeah. So it does not refer to charge. You can think of it as an escalator that carries you from low potential up to high potential. So here's another question. Thinking about the battery. Which capacitor has the largest change in electric potential? Go ahead, talk to me and get an idea. Oh yes, and capacitors are drawn to convey comparative information regarding dimensions. In other words, if it looks twice as large, that's fine, take it to be twice as large. Or the plate separation I've altered to be indicative that this capacitor has a larger separation distance. So go ahead. Which capacitor has the larger drop in electric potential? There we go. Probably beating a dead horse here.
Yes, that's really
Sadness.
What did you guys say?
Memory card is full. So the camera's really saying I talked to you.
I think what makes this difficulty different, man, is there's a hue with the amount of charge, but I think the potential difference might be the same.
Hit me with it. For which of these three scenarios is the potential difference across the capacitors? Which capacitor has the largest change in electric potential? Or maybe I should say, which capacitor has the largest difference in potential between the two plates? They're all the same. They're all the same. Because what does the difference in electric potential depend on? Does it depend on the capacitor? No. What am I really asking you about? I'm asking you about the battery. I say, which capacitor has the largest change in electric potential? Well, it's not the capacitor that dictates that, it's the battery that dictates that. I'm asking you about the battery, not the capacitor. Yay, nay? Yeah. Essentially, the capacitor is not the thing that dictates the drop in potential. Or maybe a different way to say this. What is responsible for charging the capacitor? The battery. And so the capacitor will get charged up until its potential drop matches that of the battery. So if I use the same battery to charge all three of these capacitors, all three of these capacitors will have the same drop in electric potential. But you know something's different. Does that?
I got followed all the way up until like the last thing.
All three are charged by the same battery, so all three capacitors will have the same difference in electric potential. So I guess a different way, you could think of this as being an escalator, and this is a slide, right? You go up the escalator, so you're on the first floor, and now you slide back down to the ground floor. You go up the escalator and slide back down.
How would you know if there are different batteries? Does that make sense? Like,
Oh,
obviously we know in this they're all the same battery, but what's like an example so we know like how you like to know it?
if I would denote, I guess I should probably mention something about same batteries. Different batteries, I'd probably say something like V1 and V2. You know, I'll give some sort of different subscript to it.
But if they're not like labeled, then we just assume.
Yeah, that's fine. Or if in doubt, just yell at me and say, hey, Greg.
Okay.
Yeah. And then, okay. There we go. Or maybe I would say like, you have a battery which has a potential of 10 volts and, battery 2 has a potential of 20 volts or something like that. Yeah. So the question really is, which of these three arrangements has the largest battery? You say, well, Greg didn't say anything, so I assume the batteries are the same. Go ahead and assume the batteries are the same. But there's something different. You know that there's got to be something different. And what's the thing that's different between these three situations?
The amount of charge that it can store.
The amount of charge that gets stored. Go ahead, rank them. Which one stores the most charge? Which one stores the least charge? Assuming that the batteries are the same, right? If you can tell me the most charge, you could rank them as well, right? At least in my head, a ranking exercise is the same as like identify the largest, right? You might disagree with me. You say, well, ranking's harder. Yeah. It reminds me of that. Which one weighs more, a pound of feathers or a pound of bricks? You say, which one weighs more?
They're the same.
They're the same. You know something's different though. What's different? Something? But then Something's different. Survey says, which one gets the most charge? The third one, the one with the largest area. That's why I said, hey, I've drawn these to be representative, yeah. So the largest area should store the most charge. And once you get that idea, you say, okay, well, I could rank according to area. That tells me that this one has the most. But then I go here and say, well, those two have the same plate area. So how do you distinguish between the first one and the second one? What's the other important geometric factor or geometric quantity? The distance. And the larger the distance, does the capacitance go up or does it go down? It goes up with area and it goes down with distance. So you say, okay, well, this one's going to store the most charge because it has the largest capacitance. And then this one will be the second most charge, and then this one will be the third. So I guess ranking, I said rank according to charge, but really I could have said rank according to capacitance. Right? Which one's the largest capacitance, which is the next largest, which is the last. 2C, 1C, half a C. Which comes all the way back to the beginning. I said capacitance is a measure of how much charge can be stored on an object. Yes.
Now, if the capacitor wasn't linked to a battery, if doing all that changeable.
If the capacitor is not linked to a battery, what was the second part?
How would it change the difference?
So if you charge up the capacitor and then remove it from the battery, ideally it will still maintain that same difference in potential, right? Because the idea is that when you charge up the capacitor, hooking it up to a battery, you force charge onto the plate until the drop across the capacitor is the same as the battery that you used to charge it. Then when you unhook it, so long as you don't give anywhere for those charges to go, it will maintain that potential difference. So you can stick it in your pocket and carry it around and hook it up to a different circuit if you want. Incidentally, capacitors will provide capacitors are a little bit different than batteries in that they will not provide a constant potential difference. When you hook this back up to a circuit to discharge it, it will not discharge in a constant manner. It won't maintain a potential difference and then just drop to zero. It will do an exponential decay. And I don't mean like kind of looks like an exponential decay. I mean it exponentially decays. We have a tendency when we see this line, we just call it an exponential decay, even if it's 1 over r or 1 over r squared. And no, this one's a true exponential decay. That's all I have to say about that. Okay, it's a battery question. Oh, okay, I already answered that. Okay, so sorry, that was just, hey, which one has the most charge or rank according to charge? But I gave that to you verbally. So I thought, okay, well, as promised, I said I should probably give you a list of other circuit components because you're going to run into these, and I have a tendency of accidentally using them before I actually tell you what they mean. So I thought, well, I should just tell you what they mean first, and then if I accidentally use them, then we can reference back to this. The question already came up, the difference between two parallel lines that are uneven and two parallel lines that are even. We've got the capacitor and the battery. And I've gone ahead and I've told you kind of their function. So a capacitor stores separated charges, or if you prefer, it stores energy in an electric field. And the units are F for farad. If you prefer, you could say a coulomb per volt. I guess you could say a coulomb squared per joule, and you could really travel down that rabbit hole. A battery, on the other hand, its purpose is to provide a constant change in electric potential from the top terminal to the bottom terminal. And I've emphasized in parentheses, this is a variable current supply. It will, when you hook a battery up, it will adjust whatever current it provides to quote unquote meet the needs of the circuit. And we'll have to discuss how does the battery know what the needs of the circuit are. So I'll have to go into talk about resistors and yada yada yada. That's in contrast. I don't think that we'll talk about it, but sometimes you'll see something like a constant current supply. Okay. So that is not a battery, it's something else, but a constant current supply provides a constant current, but adjusts the potential difference accordingly. And I believe some of the, did you use the boxy power supplies this last time? Use those, okay. Like it looks like a couple bricks, probably about yay big, about yay wide, yay tall, has a couple dials on it. Okay. That is a regulated power supply. And that actually, it goes two ways. It will provide a constant potential unless the current gets too high. So it'll provide a constant potential drop between the plus and the minus terminals unless you demand it to provide too much current. And then it will swap over into a current supply. So you can max out. If you take a wire and put it from the positive to the negative terminal, you'll hear a flip, light will change, and it will only provide a set amount of current. It'll say, oh, okay, you're asking me to provide too much current. I'm going to change over to a constant current supply instead. And the same thing happens if you're trying to use it to provide a constant current, and you ask it to provide too big of a potential difference. It will say, oh, and it'll turn back into a constant potential supply. So you have some of these apparatuses that will do both if you tell it to do, it can do both. You just have to tell it which one it'll do. Other things. So I think we've mentioned this, at least in passing, but I'll put it up here. Resistor, C usually represents a capacitor. Battery, I usually use an uppercase V to remind you that it's a potential supply. Okay. Resistor, you can probably guess what letter I would use. C for capacitor, R for resistor. A capital R tends to be used for a resistor. Notice it's not a squiggly line, but a zigzag line. And you can think of the function of a resistor. I should put this in quotes, air quotes. We'll say slows the flow of I. The more I look at that, the more I hate that expression. In fact, strike that from your memory banks. I don't like that. In fact, this is terrible. I'm correcting my slide. I don't like that. Let's say removes energy from circuit. I don't like the expression slows the current because that makes, when you hook up a battery to a circuit, very quickly the current becomes constant. In other words, there's zero net force on your electrons. Okay? And so that means that energy that they might pick up from the battery being accelerated by the battery gets removed from the circuit somehow. As the electron rolls downhill, it's a different way to say it. It rolls downhill at a constant speed. So if it's rolling downhill, if you have a ball that's rolling downhill at a constant speed, you say, oh, there's something that's drawing energy away from the ball. It's decreasing in gravitational potential energy, but it's not increasing in kinetic energy. There must be some energy being removed somewhere. Right? In the purpose of the circuit, that's what the resistor does. It removes energy from the electron so that the electron doesn't change in kinetic energy as it experiences a drop in electric potential. The ball that rolls downhill without speeding up. The rest of these are a little less standardized, but I'll put them in here nonetheless. We'll see this when we get into, You have a circuit component that stores energy in the electric field. We will later get to talk about not the electric field, but another interaction, which is a little less easy to get a grasp of. It still turns out to be between charges, but it's between moving charges. And that interaction we don't call the electric field, we call the B field. What's B stand for? The magnetic field. Okay. So an inductor is a circuit element that stores energy in the B field, what is the magnetic field. Yes, excuse me, units, ohms for the resistor, Henry for the inductor. Those are still SI units. Shoot, let's think. An ohm is a volt per amp. And an amp is a unit of current. We'll have to talk about that. It's a coulomb per second. So an amp is a coulomb per second. A volt is a ohm is a volt per amp. I have to break it down in my head as well. I don't remember the fundamental units. You get used to these after a while. And a Henry, I couldn't tell you what the fundamental units are. Okay, I would literally have to go. It's L didt equals V. So it is a volt second per amp. Don't worry about that. Don't let that keep you up at night right now. Okay. We'll see that later, but I'm putting it in here for completeness. The other three tend to be just symbols that you'll see popping up in a circuit every once in a while. If you see a V surrounded by a circle, that's usually a voltmeter. These last three are not necessarily standardized, but it tends to be what I use. But a V surrounded by a circle is a voltmeter. In other words, a device to measure the potential drop. Ammeter, I don't think there's a P in there. Double check me. I don't think there should be a P in there. That looks really bad. Have I been spelling ammeter wrong? I don't like this P in here. Strike that P. And Google it. Don't trust your professor on spelling. I think it's an ammeter. There isn't a P in there. Just like a voltmeter measures the difference in electric potential between two locations, an ammeter will measure the current flowing through a location. And lastly, sometimes you'll see a circle with a squiggly in it, just a light bulb. I said, just in case. I believe you probably see that symbol in lab at some point. You can think of a light bulb as just a special type of resistor. It is a resistor that removes energy from the circuit and converts that energy into light. Whether it be by heating of the tungsten wire, or maybe it does an electric transition between the conduction band and the valence band.
Does a resistor divert energy in some way?
I'm sorry?
So does a resistor like that use energy in some way?
Yeah. I mean, the resistor, what we'll model as a resistor could be pretty much anything. So the tungsten wire in a light bulb, you think of as a resistor, and what does it do with that energy that it removes from the circuit? That goes into heating up the atoms in the tungsten. In other words, increasing the atom's kinetic energy. Well, if you increase the atom's kinetic energy inside the tungsten wire enough, then it begins to glow. It begins to emit light. And so that's how you convert the energy that way. But yes, I mean, if you're doing an LED bulb, that electrical energy goes into moving, have you guys done, I guess it would be semiconductor doping. Have you guys talked about semiconductors and doping, like in chemistry class? Okay. Do you want to know? I guess. Quick, how many bonds does a carbon form? Put a carbon into a crystal lattice. 4, right? Because, carbon, right? C, right here, right? It needs 4 extra electrons to get a completed valence level. And so what ends up happening is if you put carbon into a crystal lattice, it will connect 4 bonds. So imagine you start off with a carbon crystal. So all the carbons have 4 bonds with all the other carbons. And yeah, you can do it with anything in that column. The other one that tends to be that happens to is germanium. Okay, so yeah, germanium, yeah, 32. We'll do the same thing. Now, next thing, silicon, yeah, you do with silicon, but not as often. So you have carbon or silicon or germanium, and you have crystal lattice, so 4 bonds. Okay. Now the next thing, to do what's called doping. Okay. This is a technique. You basically will say we take boron. You could do it with like phosphorus, or you could do it with boron. One on either side. So you could go down one, or you could go up one. And what you do is you take that crystal of carbon and you put it into an atmosphere of boron. You put it into a chamber. You pressurize the chamber with boron gas. And what happens is every so often, one of those carbons in the crystal will be removed and a boron will take its place. Okay. That's called doping. I don't know, have you heard this term? Okay. Yeah, so it's called doping. You take a crystal and you remove some of the carbon and you stick it in something different, like a boron. Now you notice that boron, because it's one less, the boron will have one missing electron. It is one electron shy of a full valence shell. So what does that mean? It means that it would like to grab an electron easily. Like to grab the electron. If it could, it would like to grab an extra electron so that it has a full valence level. Of course, in order to do that, it means it has to snitch it from some neighboring atom. And the neighboring atom wants a full valence level, and so it snitches, and et cetera, et cetera. So what this does is it reduces the resistivity of the entire material. Every atom in the material wants this extra electron, so it very quickly grabs one when it sees it. Yeah?
Have you ever seen like the molecular views of Damascus steel?
Yeah.
Like they actually, it was made like a few thousand years ago, and we still don't know how to make it.
Oh.
But the people who made it, we've taken molecular views of the stuff that's remaining, and it somehow formed carbon nanotubes. Like it's 6 groups of carbon, like forming a tube structure.
Okay.
And like if you've ever seen like pictures of like Damascus steel on the internet, it looks like liquid metal, but it's like it's like 10 times stronger than carbon fiber.
Huh. I'll have to look
Like
this up later.
ridiculous. And even after a few thousand years, we still don't know how to make it.
Yeah, I mean, material science is a real big field. And from my point of view, it's a lot of guess and check. I think this might work, and then you check it, and then you. So what happens is you take this carbon structure, you would replace some of the atoms. It doesn't have to be a lot, like maybe a 1,000%, maybe even less than that. And because of that, now you've created this situation where you have these atoms that want to grab an electron very quickly. If you get an extra electron, it wants to grab it quickly. And it grabs it from its neighbor, and so the neighbor wants an electron, so it reduces the resistivity of the entire thing. You could go the other way. If you dope it with phosphorus, then you've added an extra electron that nobody wants. So then it's like a game of hot potato, right? The phosphorus has this extra electron, and it tries to push it off on a nearby atom, which tries to push it off on a nearby atom. And so you pass around the electron very quickly. So again, it reduces the resistivity. Your LED light bulbs are basically made out of these kind of materials. So what happens is that essentially there's a very small difference in energy between the valence level and the conduction level, or the valence band and the conduction band. And so that small difference happens to correspond to the energy of the visible light. And so when you have, for example, if you do the boron doped semiconductor, when it grabs the electron, that electron falls into the valence level and it emits the light. And that light happens to be visible. Of course, the carbon next to it wants one, and when it falls in, and yeah, so that's how the LED bulbs work. No, you've never heard that? You should go to Dr. I don't know, who does materials? It would be, I guess it would be like inorganic chemistry. So who teaches inorganic?
Dr. Philip.
Yeah, okay, so go to Dr. Philip and ask him about doped semiconductors. No? Yeah, let's get into resistors real fast. So conceptually, qualitatively, resistors. Everything else being the same. So analogy, but everything else being the same. Yeah, in terms of traffic density and all that kind of stuff. Which road will you be able to drive, I don't want to say faster on, what I want to say is, if you're going from destination A to destination B, and traffic is roughly the same on both roads, which road are you going to be able to travel faster on? Which road are you going to be able to get from destination A to destination B faster on?
Interstate.
The interstate. I mean, say everything else being the same. So let's say that this is still 70 miles per hour, this is 70 miles per hour. Now, I couldn't find a picture of a 2-lane road with a truck on it. I'm sorry. This happens. Apparently, there are no 2-lane roads that have trucks on it, except the one that I drive on. Right? The minute that I get on 7 and I want to go to North Vernon, there's like 10 semi-trucks and a farm vehicle. And, yeah, grandma. Grandma, get off the road. I love you. I'll call you later. Yeah, you say the interstate. Why? What about this road makes it easier for you to get from point A to point B? Everything else being the same. I'm sorry? More lanes. Right? If you're on the interstate and you get behind farm vehicle, you have the ability to scoot over and keep going. Whereas if you're on 2-lane road and you get stuck behind farm vehicle, you're smelling hog for the next 15 miles. Quick, kids, roll up the window. Okay. So the issue is, first of all, I want to say it is the more lanes you have, the easier it is for you to get from point A to point B. You have some flexibility of moving laterally if you want. So say for lack of a better word, the resistance goes down. Right? You can get to point A to point B faster, lower resistance. Okay. How about this? Okay, yeah, as the number of lanes increases, I was thinking area, and that's just to get kind of towards where we want to go. But as the area goes up, your traffic flow goes up. You have more lanes that allows you to shift around. How about this one? You're going from point A to point B, and let's just make it, let's say point A to point B. Except for this situation, point A to B is, that far, and point A to B is that far, for the second situation. Which situation is going to take you longer? The longer road, especially if there's traffic on it, right? I mean, which traffic jam would you prefer to be stuck in? Survey says this one. Shorter traffic jam means that I should be able to get from point A to point B faster. So I guess the second way to say it is the length of your lane goes up, the traffic flow goes down. Right? The longer the road is, the longer the traffic jam is, the decrease in the traffic flow. Oh yeah, I had an example. Oh, yeah, I guess you could do, oh shoot, I forgot. You ever try this? Do they have coffee stirrers at the CC? Yay, nay. I mean, I would hand these out and we could go outside and try it, but with the COVID times, you don't want to be touching straws even though they've been in a box for the last year. All right. But do they have coffee stirrers at the CC right now? I don't know if they would or not. Should go and check. If you have ever done this, this is a pain in the rear. I mean, I know, big football conference champion. Go and try to walk around with a coffee stirrer in your mouth. And by that, I mean right? No. Like take a coffee stirrer, put it in your mouth, and try to walk from the CC to your dorm. I dare you not to pass out. And the same thing, try it with a straw. I would do it, but you'll see me get red in the face, and then I'll pass out, and then you'll have to. Yeah. So try this. Go in the CC. Grab a straw, which I think they definitely have. You see it, you know? See if you can find some straws in the CC. Certainly they have them downstairs. See if you can also find a coffee stirrer and just try it. Try breathing, put it in your mouth and try breathing only through the coffee stirrer, and you'll notice physically how hard it is. What's going on here as compared to the straw, you increase the area. So not only does it work with something like traffic, but you can try it, yeah, with breathing through a tube. And then after you convince yourself that the area does play a role, cut the tube in half. Take the coffee stirrer and cut it in half, and then try it. I think you'll find that it's a little bit easier. And again, I'm sorry, I had coffee stirrers in the office, but I thought it wouldn't be appropriate to pass them out. Now, if you're really jazzed about one, that's, take your own risk, and I can give one to you. No? Yeah, try it. Or even better, don't tell your parents and just try it on them. Watch them pass out. Okay, so what are we getting at? As the area goes up, the flow goes up. As the length goes up, the flow goes down. So just like capacitors, we're trying to get an idea about how does the geometric shape of a resistor affect its resistance. Okay. So we get something like this. I'll just put that up there. So if you want to know the resistance of an object, it is, I guess for lack of a better term, we'll say defined as the length of the object divided by the area. We said, hey, as the area goes up, our traffic flow goes up. That means our resistance goes down. Hey, as the length of our traffic jam increases, that means our flow decreases, and so the resistance goes up. So resistance is inversely proportional to the area and proportional to the distance.
The rho, what was that stand for?
Yeah. That's the general one is, yes, this is a Greek letter rho. And let me write this down real fast. They said the capacitance is essentially, I'll put epsilon times the area divided by d. And notice I put epsilon, not epsilon naught here. So that epsilon depends on the material. When we're dealing with the resistor, it's the same idea. This is called the electrical resistivity, and it is a property of the material. So I've put two down here for you just to give you an idea. So things like metals, I have copper and iron. The resistivity, that rho value, is on the order of 10 to the negative 8. For every meter's worth of metal, you get 10 to the negative 8 ohms of resistance. There's a couple of extra things in there, but that's essentially the idea. So you get some material property, and then after that, you have the physical dimensions, L and A. This feels a lot like the capacitor, except that for capacitance, you notice that it's proportional to A and inversely proportional to D. For the resistance, it's inversely proportional to A and proportional to, I'll say L, but you could say D as well, the distance. So you have a copper bar, for example. Say you wanted to know what's if I put a potential difference across this remote, how can I determine what the resistance of this remote will be? What you could do is say, well, it's made out of, I don't know, aluminum. I think it's metal, actually. I don't think it's cheap plastic. I think this is metal. And so we'll say aluminum. Well, what you want, if you want to know the resistance of this object as you try to pass current through it, you take the area, okay, and it's called the cross-sectional area. Pretend that you take a big saw and you slice it to get the cross-section. Current's traveling this way, so I got to slice it that way. Okay. You take this area, that's what goes right here. Number of traffic lanes. As the electron comes in and tries to navigate this traffic, it is allowed to shift lanes. There are more lanes for it to move around in. So that's what goes in right here, that A. Second one is, okay, well, the length would be the physical length of how long does it have to travel for. The longer that this remote is, the longer the traffic jam and the longer it spends trying to navigate around to get to the other side. And that would be that dimension, that L. So the upshot is, if you need to create a resistor, you can just go out, get a material, cut it to the right sizes, and boom, you've got your resistance. I have no idea what resistive, like, I'm sure that that's something that some manufacturers do. Just take stock material, cut it down to the right sizes, package it up, and boom, you're done. Oh, okay, anyway. I'll leave, well, how are we doing? Okay, I'll leave with one last parting comment, and this is jumping to several slides later, but we have 2 minutes, and so I thought I'd throw it in right here. You remember, how can we combine capacitors? If I could put capacitors in parallel, that is effectively increasing the area, which means the capacitance goes up. If I put resistors in parallel, that is like giving more lane, that's like adding lanes to your highway. You've given more options for the electron to move. It could go through resistor 1, it could go through resistor 2. You've increased the number of lanes, which means the resistance should go down. You remember those rules for combining capacitors? I said, hey, if the capacitors are in parallel, the overall capacitance is given by the sum of the individual capacitors. Okay? That's in parallel. That's because this area is in the numerator. Right? How about resistors? If I put resistors in parallel, what do you think that'll look like? Just curious.
1 over R1 plus 1 over R2.
Yeah, you end up with this 1 over R1 plus 1 over R2. Okay. So those rules of combining capacitors will also apply to resistors, bearing in mind that when you put resistors in series, that's effectively increasing the length. That's the analogous of putting capacitors in parallel. We'll pick up there. I'll cover it again, but we'll pick up there on Friday. Hey, thanks for your attention. I'll see you Friday. I will email you this afternoon.